as usual, I'll start from the previous episode. So what did we do before? And essentially what we are doing is information theory, and we measure information by uncertainty. So information, quantitative measure of it is how much it lowers the uncertainty. And the simple case is when we have equal possibilities, or we don't have any extra information about real chances of these probabilities, and then our uncertainty as a quantitative measure is a logarithm of n, and this is and we usually take it, let's take it this n log 2, namely this is the number of yes no answer, even though it could be non-integer, which is a measure of uncertainty. Now when we know that there are, I'm reminding what we did before, so you did not. When we have different probabilities of different possibilities out of here, pi's, how we measure uncertainty? We now measure it on average. We take a very long string n with a length n, string of symbols, and we ask what is the number of typical strings like this. And the number of typical n strings, we say that it's exponent n s of p i's, and this s, as defined by Gibbs, was the sum of pi log, in this case logarithm because we take exponent, or we can take here 2 and it will be log pi's. So if this is a typical number, then the uncertainty is a logarithm of its typical number, and divided by n, it would give us s, which is information per letter. That's how it appears in this case. Then we say yes, but generally, if we're talking about language, every next letter brings less information because it's somehow dependent on the previous letter. That was already second lecture. And there we introduce the pij, which is a probability of j under condition of I. It's a probability distribution with respect to j. Sum over j over all j is equal to unity. And this brings the idea of conditional entropy. That much next letter brings us, and we call it s of ji, but it actually does not depend on specific values. It's a sum over all i's of pi's, and it's a sum over all j's of p of j under condition of I, and log p of j under condition of I. So this is a conditional entropy, and it's generally less, as we have seen for English language. This is about 3 times less than this, and this is less than that. Every time we brought extra information, here we brought pi's, here we brought pij, which is a whole matrix of which pi is an eigenvector, we lower entropy further and further. And this for a while looked like a technique, more or less, for communications and linguistics, and then suddenly application of this simple set of notions exploded. And let me show you how it happens. And the central quantity here is this conditional entropy or conditional probability, which is a very straightforward thing. Let's say that we have B, that's some quantity, which could be an input of a channel of communication, and A is an output. But it could be that B is a physical phenomenon and A is a measurement, is what we read on our device. or it could be that B is a memory which we encoded somewhere, and A is a reading that we retrieved it from where. It's a very, very general scheme. And now that's what we have. That's what we don't. So now we ask, what is actually, now that I know the value of A, what is an uncertainty in B? And then I, of course, must say that this is S of B under the condition of A, right? So generally, it's a sum over all P of AI over I, sum over J, P of B J AI log P of B J AI. This is with a sign minus, right? So now what is important, that this quantity is generally less than uncertainty which we had before, but not for every AI. It's an important. Only on average, only when I sum over all my measurement, because for a given measurement, it may be a very skewed probability distribution which would have higher. So as communication people say, information does not hurt, but only on average. So now, that what remains uncertain after we get A, and that what was. So any measurement or any message we have received here bring a quantity which is a difference. This is the most important quantity in this course, and generally in all the in information theory, without any exaggeration. This is the most important quantity. Absolutely. And it's called mutual information between A and B. That's its definition. Okay? Now, it's by construction it is positive, and yet it could be proved that it's positive. For this, you actually take this and use convexity of this function. I won't do this, but it's a very useful exercise to really prove that even though for every value you would have this entropy in general could be larger or smaller than this, when you average over several values, it's enough to have 2. You can prove it for 2 and see how it works. Now, I can write it in the following form. S of B is a minus P of B log P of B, J, and the sum over J. Let me just, for the heck of it, write it that it's also a joint probability of AI and BJ, and I sum over all I and J. Also, what is standing here is nothing but a joint probability of a pair AI BJ. Generally, it's called chain rule. It's pretty trivial. By the way, this Laplace says that probability theory is common sense expressed in symbols. So, generally, if I have independent probabilities, right? P of AI and BJ would be P of AI times P of BJ, right? But if they are dependent, what you need to put here is that this is the probability of AI. It's usually written from the right in the Hebrew. We actually already did it on the second lecture. Probability of BJ under the probability AI. So what stands here is again a joint probability of Pij. So now I may write this thing as following. It's a sum over Ij minus probability of AI Bj. And what would be here would it be log of this P of B, let me erase the minus, so it will be this of Bj, and what will be here P of Bj under AI, which came from here, right? But look, this, according to this formula, is nothing but joint probabilities divided by P of II, right? So what we got a beautiful symmetric formula. It's now symmetric with respect to ij, and is nothing but S of I plus S of B minus S of A and B. Sometimes people draw what is called Venn diagram to visually illustrate it. So if you have something that you can call, this would be S of A, all right? It's kind of measure, right? So you can look at it as a set. And then you can have S of B, right? What is here S of A plus B? There is a set where they are interdependent, and there is an envelope of it. So this red one outside is S of A plus B. And then where is the mutual information? It is in this overlap. It's S of B plus S of A minus S of A plus B, which is this one. You just visually see how any interconnection, so this is I. And of course, because originally this was this, so I is S of B, and what is this? It is this, right? It's a conditional, it is S of B A, and of course this is S of A under B. So that's a whole symmetric Venn diagram, and it's a most used and usable formula and a notion. It's mutual information. So even though A and B could be very asymmetric, right? One be position of atoms, another will be, numbers on the measuring device. One could be dollars, another could be bits. And the entropy could be vastly different by many, many orders of magnitude. Their intercorrelation is symmetric because it's intercorrelation. And of course, it's clear what would be a limiting cases. In the limiting cases, when there is no overlap, no correlation, mutual information is zero, it's non-negative, and it gives us all we want. Now, the first case where it turned to be so important was the famous Shannon noisy channel theorem, which poses the same question that we asked before: how much information a channel brings? Okay, we say that for every measurement of A, on average, we get this information. It's called information, right? It's this minus this. But this is kind of not a theorem. It's a very, very hand-waving argument. And to appreciate it, we'll consider simple cases and not a general proof. So the idea, first of all, if you have B's, different values of B's, and there are, for each one, this is A, this is B. So this is input. So there are M values of A. And for this, there are M values of A. And for this, there are M values of A. What is the information? And everything is equally probable. Okay? So every value of B is equally probable. So we are obtaining M's. What is the rate of information that we obtain? Rate is always an entropy, right? So we need to ask which entropy we obtain. S of A S of B, some conditional S of B. First of all, from this viewpoint, we're just getting some values of it, right? So generally, the information rate would be equal to S of B, right? Which is, if I have here n values from 1 to n, on the other hand, I may say that this is the logarithm of the entropy of A minus entropy of A under the given B. But this is log of mn. That's that many values of A I have, right? And this is minus log of m. Because when I get it, there is still uncertainty. When I get any A, there is still uncertainty. And so it's again the same logarithm n, which is S of B. So in this case, S of B under A is 0. And in a sense, it is still technically not a noisy channel. We don't make mistakes here, right? OK, let's now turn the tables and say, OK, let's now look at this channel. So let's say I have here one k, and there are L's on the B side for each one. Now, we cannot, when we obtain A, definitely restore B, right? From the viewpoint of measurement, is not any definitive measurement that would give you. It's still, again, it's a beauty that you could look at everything from the viewpoint, whether it's measurement or retrieval or prediction or in channel of transmission. And what Shannon suggested, he suggested look not at statistics here, but at this thing, namely, what is the channel itself? And he formulated his theorem as a state. And again, I'm not a mathematician, so I'm not formulating theory. I'm loosely explaining the way I understand it, that for any channel, if there is a non-zero mutual information between input and output, you can asymptotically reach an error-free transmission. For this, you need to choose correctly the probability distribution of your inputs. That was the idea. So what it means, that if I would choose my inputs equally probable, like I did in this case, right, that would be wrong because I would be making mistakes. In this case, it's trivial and immediately evident that I just need to choose my every input from every group and not any other. So if I choose this, the probability of this must be 0. If I choose this, the probability of this must be 0. And then I can reach an error-free transmission. And generally, Shannon defined a capacity, and it is called a Shannon capacity out of respect. And this is defined as a maximum over all P of B of mutual information between A and B. And this is a symmetric information, right? So in this particular case, it's clear what must be P of B. But it's also true in a more general case. And so maybe I'll show. And his argument was that, let's present again. So if I have a channel like this, what would be its capacity? I have here entropy 1 bit, here entropy 1 bit, and the capacity is 1 bit. Like everything is in bits. Now, if I have channel like this, what is the capacity? It's either 2 or 1, because here I have 2 entropy and here I have 4. But what would be the capacity? It's an illustration of this formula. What is S of B here? 1. It's 1/2 log 1/2 plus 1/2 log 1/2. It's 1. So it's again C equal to 1. Okay? And if I have something like with intersections, for example, something like this, one, two, three, four. How many I have? 5. What would be the capacity here? Again, let's write it. C is S of, let's say, S of B minus S of B under condition of A. What is S of B? Do we have 5 or? Yeah. The conditional entropy, well, there must be 6. 1, 2, 3, 4, 5, 6. Okay. So if this is log 6 and this is log 2, because for each one I have 2. For each this I have 2, and for each z I have 2. So my conditional entropy is a logarithm of 2, and my total entropy is a logarithm of 6, right? So what I will get here is a logarithm of 3. That's how you get this conditional entropy. And the general idea, in a very general case, that even when your channel makes errors, you can lower your rate so that you get extra bits, your rate of useful information. So you can get extra bits to correct for these errors. This is essentially the idea. And again, let me illustrate it in a thing which really makes error in a random way. So I have 0 and 1. I have 1, or 0 and 0, 0, 1, and 1. So this is a channel. It transmits 0 to 0, and then transmits 0 to 1, but it can make an error with a probability q, right? That's how you, yeah. So this is, yes?
I have a clarification question.
Yes?
For your red diagram, do you have like, over here, your first for the channel, do you have one of K letters, and each of the letters can be one of L letters?
No. In this case, I'm working in bits. So what I'm doing, I have what is called binary channel. So I need to say it a little bit more in detail. So I have a binary channel. It has 2 possible inputs and 2 possible outputs. The simplest case, I transmitted error-free. 0 goes to 0, unity goes to unity. Then I get 1 bit per symbol, if I choose them with equal probability. If I choose them with an equal probability, I would get Gibbs, right? But my capacity is a maximum over all probabilities. Now, this is a little bit more complicated case. I have 1 bit input, but 2-bit output. So in my output, there is 1, 0, 0, 0, 1, 1, 0. Okay? In this case, I have 4 outputs, but the rate with which I obtain information is still 1 bit per symbol, because essentially, whether I get this and this, I still read this. Whether I get this and this, I still read that. Okay? And now a more complicated case in which everything is mixed. For every output, I have 2 inputs. For every input, I have 2 outputs. That means that my mutual information is the entropy of either output of input, it does not matter, which is logarithm of 6, 1, 2, 3, 4, 5, 6, and minus conditional entropy. That's how it works. And yes, more question at this point? This is really simple but important, and this is, as they call, the most important statement of information, of communication theory. Not the whole information theory, but at least of communication theory. Okay, so now let's treat this, where we do have a real, this all are dynamical, right? So this kind of with the fixed rules. But now I have a probabilities of mistake. Means that P of 1 under condition of 0 equal to P of 0 under condition of 1 equal to Q. Okay? So now, in this case, let's compute, and again, this is B and this is A. Let's compute conditional probability of what? B of A of B, doesn't matter. A under the condition of B. Okay? This is the same as A of B of A. And if you compute it, it asks you what, if you fixed this, what is your degree of uncertainty? Well, your degree of uncertainty is that you have two possibilities, right? And those possibilities are that with probability Q, you have log Q, and with probability 1 minus Q, you have log 1 minus Q, right? That's your two possibilities, and that's the entropy of this distribution. Let's call it S of Q. Okay? And now, if you are interested in what is your capacity in this case, it's an entropy of this binary channel. And the entropy of this binary channel is determined by its probability, and its maximum is unity if I equally send signals, and there is no reason to prefer one or another. In this case, there was a reason to take asymmetric probability distribution. Okay, and it will be 1 minus S of Q, this S of Q. Okay, and this is now a very practical formula. For example, if you take, let's say, Q equal 1/2, what we expect of a capacity of a channel without computation? Look at the ceilings and say, if with probability 1/2 I am making an error, could it be error-free transmission even asymptotically in this case? Could I transmit anything through a channel where my output with equal probability means 1 and 2? No. Is it evident? I mean, like here. Indeed, if Q is 1/2, then S of Q is 1/2 log 2 plus 1/2 log 2 equal to unity. So if S of Q equal to unity, the capacity is 0, you can transmit anything. On the other hand, if your Q, for example, is 10 to minus 3, and we are now, in fibers, we tend to have 10 to minus 12, but even at 10 to minus 3, when you compute this, you get C equal to 0.998. So it's kind of exponentially fast goes to this limit. Okay, and again, the general idea, as always, is that this determines the total number of possible outputs, and you need to divide it into groups, more or less, which correspond to uncertainty. So the way that I'm not going to give you a proof, but the technique is always the same. There is one idea which is recycled in the science, the idea of typical sequences. So you take a very, very long sequence, and you ask how many typical sequences, and then you take them into groups, more or less like we did here, and you divide into these groups, and then on average you claim that whatever typical things happen, they are irrelevant in the limit of n going to infinity. Okay? Is that clear? Questions here? Because you need to understand that I'm not giving you a normal course where I would spend like 2 hours on this, and then you would have, a problem-solving session where you can really compute capacity for 5, 6 channels and then fill it. So it's something that I'm giving you a feeling of it, but not real knowledge. Okay? because I really want to show you a big picture. So now let's move on, how people use this. And but before, I'll show you something which is even more maybe simpler but more generic, and it's the idea of using this chain rule in a very, very creative way, and from it we'll see the generalization of it. So let me write my chain rule in the following form. Probability of, how I call it, H and E. Yeah, okay. H and under condition E times probability of E, of course, is equal to the probability of E under H, probability of H, and this is the joint probability of H and E, whatever is H and E. And now, a very straightforward and extremely useful way of applying what let's call this evidence and this hypothesis. Okay, and it's called bias framework, and it's conceptually changed the way we do probability theory, even though it's trivial in a sense. But the most trivial things are most powerful. So let's write this formula in the following way. Probability of hypothesis being true under a given evidence is the probability of hypothesis without any evidence or data, or at least this piece of data, right? And it times P of E H divided by P of E. It's bias. Now, it's totally trivial, right? It tells you that you need to take a prior probability of what was the probability that this statement is true, and multiply it by a quotient, which increases. Generally, this is larger or equal to unity, right? So if there was any probability of this evidence, then it's this. And then you get a posterior probability. For example, your hypothesis is that there is a vast international conspiracy to increase power of governments. And your evidence is COVID epidemics, right? It's piece of evidence, right? So now, if this hypothesis were true, namely there was such conspiracy, this probability is very close to unity, right? If there is an international conspiracy, then it's very, very likely that some kind of a global event which increases the power of government happened. And most people stop thinking at this point, which is called, by the way, inversion of probability. You need the condition on this, and you think about condition of that. But this could be extremely small, right? In particularly, what is really needed, it is this quotient, right? That's what you need to find. Let's say we have a hypothesis and it's negative, namely that we have H1 and H2. So in this case, I would say that H1 is my statement that there is a conspiracy, and H2 is my statement that there is no conspiracy. Okay, then there are only two possibilities, and here in the denominator, what I would have is the following. I would have P of H under H1, probability of H1, and plus P of E H2, probability of H2. That's a little bit more useful formula. Let it write it in the following form. We divide everything by this, and so you can write it as 1 over, I just, as physicists like, we want to get everything into one-dimensionless number, and then we look at this number when it's small, or in this case close to unity. So that's what I'm doing. I'm just dividing, and I will get the following formula. It's P of H2 divided by P of H1 and P of E H2 divided of P of E of H1. Okay? And now it's you really want to find the data to do type of experiment. Most of irreproducibility crisis in sciences is related that this formula is not used or used incorrectly or somehow, you know. So in particularly if you are interested in in a case where, for example, P of E of H1 and P of E is as close to unity, and P of E of H2 is much, much less than unity. So in this case, or over here, one is much probable than another, right? But they are additive. So working on a small quantity, it's not something which gives you much information. Then if you really look at it and you say that this is a very small, now this is, okay, so you want this to be larger, so you want this to be smaller, right? And so you want to design it in such a way that you would work in, if this is already close to unity, right? That's here you need to work. You need to work. This is not under your control, right? Your experiment or data analysis or whatever, it's about gathering evidence. So you ask yourself which evidence you want to work on, and then you see that, for example, if you're working on a very improbable hypothesis, so you try to work with its alternative. So you look for a data under the condition H2, which are your alternatives. So in this case, you would ask, if there would be no conspiracy, what would be the type of probability of seeing this and this? And this is where really you get crucial information, where to believe your hypothesis or to reject it. Okay? This is a general framework which is very useful. Let's see, for example, also another COVID example. I think it's something which I liked. My wife worked back in pharma, and she actually taught me. She's a chemist, but she knows these things. She taught me this because initially I misunderstood how it's possible that the same chemical test in the same lab works better with like in 21 than in 20. And she explained to me, and I want to explain it to you because this is a piece of simple mathematics which explains everyday phenomena. So let's say we're doing a test, right? So our hypothesis is that you are a drug user or you are COVID positive or whatever, right? So consider data which consider that the probability of E under H1 is 199, which means if you get a positive result, it's 99% that this is a true result. Okay? And then what is called a false negative, the probability of E under H2, it's also 99, right? So if you get a negative result, the probability that you are still positive is 1%. Okay, that's called specificity. And so now let's see how it works. Apparently, by the way, this is H1. Yeah. This is P of H1. Okay. So now let's see. And apparently it depends. In a very we defined everything except we need to say what is the probability of you generally being ill without any data. That's a percentage of people who are drug users or COVID positive in the population. Okay, and let's say take it 10 to minus 3, 0.1%. So pH of 1 is 10 to minus 3, 0.1%. Okay? Well, times 5, 0.5. Okay? So it's 0.5%. Now, if we plug all these numbers, this here, this here, this here, into this formula or into that formula, and I spare you the computations, then the answer would be, in this case, 0.03. Where is the answer? 3. Okay? I think it's worth contemplate and look at it. So at the beginning of pandemics, 0.5% of population had this virus. You get a positive test, which is a very reliable by any standard. Less than half is your probability that you're positive. And now, when this number is 1/2 or 1/3, of course, this is now the probability is approaching 0.99, where it should be. Okay? This is something which is really show what is the importance of priors. It's the same with the drug users. For example, in the society, well, in most normal societies, there's not a big percent of people who are drug users. You go, you do reliable test, and then you multiply it by the probability, and that's your probability. This is something which is apart from trivial mathematics and some simple social effect. It's something I think important psychologically. We aren't very well designed to treat ourselves combinatorically or statistically, or consider us as just a sample out of unskewed sampling size, right? Which is why I believe that bias framework is so important. It shifts the understanding of probability from a classical, Bernoulli, Laplace, and all this, where we treated probability as a result of reproducible identical events. There is nothing reproducible identical about doing a test to a single person or trying to estimate probability of a global warming. We don't have different planets. We don't have ensemble of planets. Even with this planet, we don't have ensemble of initial condition under which we can average, because we cannot repeat the evolution of the Earth from the same data. And so the bias framework orients us to use expectation and correction of expectation, which is a totally different use of the same mathematics, right? It tells that you have a prior expectation, then you do your data collection, and that changes your, of course, you may say, this is subjective. Yeah, well, it is. But then when you do it many, many times, when you do many experiments and you correct, then you will see whether you approach unity or you go away from unity. And that's what really matters, like Lyapunov exponent, which we discussed in the dynamical chaos. Okay? This was the second part. Is it okay? Questions? Was it trivial for somebody? 0.33?
No.
Yeah, well, it is trivial to my wife, for example, but this is because she knows what is specificity. And okay, and now the last part of it is okay, but how to make the hypothesis, right? This is a most straightforward. No, I'll better go to the left. And so now, because everything hangs on getting right distribution, let's ask how actually we can make a hypothesis about distribution when we have data. Of course, we like to make hypotheses even before data. One of the, I need to say this because it's another thing which I was really surprised. It seems that our brain works this way, just before Laplace and bias and all this. And this is something which is not now a hypothesis. This is really a piece of hard experimental data. Our brain does not get a sensory input, sends it into the brain, and then forms something. When you measure the amount of, like you're sitting in a dark room, your eyes are closed. You open your eyes, switch on light. At this moment, the approximately comparable number of signals goes from your brain to your sensory, to your eye, and from your eye to your brain. Another piece of, it's called predictive mind now. There is a couple of books very clearly written about it. Another thing which we know since 15th century is called binocular rivalry. You maybe heard about it. If you just make it like this, and you put here a man and here a woman, or a dog, they usually say dog and tree, right? Somehow less sensitive. So if you put dog and tree, then generally without any priors, your eye would see dog or tree, or one or another, but not both of them. But if you were primed, namely you've seen several trees before it, you won't see a dog at all. Which means you do see it. I mean, on your retina you have a dog, and the respective pulse goes in. It's just blocked by brain, which has a hypothesis what we're supposed to see. And this is really tells us that this is a very powerful formula which kind of has a relation to more than we would. Okay, and now what I really want to do a little extra. So how we may get from the data the true hypothesis, right? So for example, I am looking for some probability distribution. Let me call the random quantity x. So I will be looking for my p of x. Or even in continuous case, let's call it rho. I'm looking for rho of x, but I don't know it. What I do know, I do some measurements. And when I do measurements, I obtain some quantity which are averages. So some quantity, I take some function of x. I'll probably call it R capital. Yeah. Oh no, I'll take it. So I have some function, and and what I can measure average of it, which means that technically I am measuring the quantity of some r of x, rho of x, dx. And there might be several of them. I runs from n. Let's say I did it. What is the distribution that I need to assume given these values? This must be a distribution which would give me these values, means that contains the truth about my data, this truth, and it must be truth and nothing but the truth. So help me God. What it means, nothing but the truth? It means no other assumptions need to be made. It means it must correspond to a maximal entropy under the condition of these given measurements. Okay? That's the way entropy determines distribution, and not only in equilibrium. In equilibrium is with this quantity or integrals of motion, but it's a very general framework. The truth and nothing but the truth. That's a statement about maximal entropy, which is again a common sense. You want your distribution to be open to all other measurements, maximally open. You don't want to put something into it which is not into your measurement, which technically means you all learn Laplace. Laplace method says that your entropy is an integral of rho of x, or some, let me write, an integral dx. So what you need to do, you need to consider by Laplace method a functional and take lambda I Ri of x, right? Sum over I, which means that which means that what stands here is the integral of Ri of x rho of x dx. So you need to look for the extremum of this functional, right? This under the condition of this. This is unknown factors which you obtain by making it normalizable. And so when you vary this with respect to rho, what you would get logarithm rho equal to sum of your Ri's of x with lambda i's. So your rho is exponent minus sum of lambda i's Ri's. That's rho of x. And 1 over z, I don't give you this. You can look in the notes for this. Okay? If you measured temperature, which is the sum of kinetic energies of molecules, you get Maxwell distribution, because this would be V sum of Vi squared over 2, and that 2 will be temperature over m. If you measure positions, you would get exponential function of position. So depending on what you measure, you get the respective function. Okay? So this is the most general framework. Now, when you vary this and you get this equation, it could be that it has no solution, because your solution must be everywhere positive and normalizable. It happens. Then you go back to the lab and you check where you made an error in your computations, right? But this generally, if it has a solution, it's the only solution. You can actually prove that this maximal. There are some degenerate cases where you can have, and then you make a sum of if there are two maxima of the same height. But this is a very general framework which tells you how to get. And now what happens when you do extra measurement? So for this distribution, you compute entropy, which is minus rho of x log rho dx. And let's call it S naught. And you do another measurement. So now you would be lowering your this after you did a measurement. This was before you did a measurement. And this is the information that measurement brought, which is the mutual information between your system and measuring device. Okay? And then a very important piece of science and computation, which I start now and will continue next, is how much it costs to make a measurements. Are there any natural limit imposed on it, or is there any price? You remember that at the beginning of the first lecture, we asked, is there any natural limitation on the efficiency of thermal aging, right? I'm burning cesium, I'm asking how much work I can get out of it, and then I discovered that there is this quantity which we now use every second minute that determines the efficiency. So, for example, I may ask, do I need a work to make this change of entropy to acquire this information? And now, what relates energy and entropy dimensionally? What quantity? If I divide or differentiate entropy with respect to energy or energy with respect to entropy, what it is? It's a temperature. And temperature dimensionally, it what relates energy and entropy. And so we may say that now if there is any restriction or price or whatever, it depends on what temperature I'm working and doing my measurements. And in particularly, as we discussed, the quantity which combines both energy and entropy, it's called free energy. It's an energy minus Ts. Let me remind you what it is, because we'll return to it where we'll be doing Maxwell-Demon and Landauer principle and limit on computation the next lecture. So it tells me that the free energy I am free to use to do work is not energy which is in my system. It's an energy minus T times entropy. In 19th century, Helmholtz argued that to keep system at a finite temperature, I cannot use all its energy to do work. That's why my energy is less. Now, in 21st century, we argue it differently. We say this is a measure of our ignorance. So because we don't know something about system, then we naturally cannot use all its energy. That's how much we don't know. As long as we learn more, we get this delta S, we increase free energy, right? So delta F coming out of measurements would be T delta S from here. And the first law or energy conservation tells us if you get an information which diminish your free energy by this, you need to do work which is at least that much, right? This is actually what Schiller told Einstein in the corridor of Berlin University in 1924, discussing Maxwell-Demon. But that's what we'll talk next. So this is essentially the statement that our degree of ignorance is something which diminishes free energy. Any acquired information increases the work we can do, and then it costs work. And then you look back into Maxwell's diary, and Maxwell in 19th century says exactly this. He says that if we would know everything about system, the difference between work and heat would disappear, which is essentially this meaning. That's the end of this lecture. It contains three important elements. I want to remind you. We started from purely informational stuff, and we use a conditional probability in a somewhat new setting, not about letter after letter, but in a very, very generic way of relating input and output. And what we discovered is the totally universal quantity, which from now on would appear. Today's lecture is a summit. From then we go down, just use, because we have everything now in our hand, except one quantity, which is a small generalization. We define mutual information, and this is the most important formula here. This is the central formula of this course. Then we will use it to bacteria, stock markets, and all this. We gave several examples, and then we also use conditional probabilities to describe this Bayesian framework, which tells you how to check hypotheses. And we ended up saying how to make hypotheses out of your data, the truth and nothing but the truth. Okay? Good. That's it. Questions? Yes? Yeah, let me reproduce the question. The question was that in one forms of encoding, there are a way to encode information in the phases of a signal, and then the encoding is used in such that the probability of opposite phases, of phase and antiphase, is equal. This is essentially to maximize. The answer is that this is essentially to maximize mutual information between input and output. And the first example of it was discovered by analyzing the eye of a fly. It essentially means that you want to to maximize the rate of information transfer, you want to use all your dynamical diapason more or less equally. Okay? And that maximizes the rate of transfer. Technically speaking, in this case, what you do is that this is set, so you maximize that. So see you in a week, and we'll go downhill from there.